Through the Gaussian distribution, you can also calculate or determine what the mean or average is, what the variance is, what the standard deviation is. And these are standard equations that one can use to calculate these from any set of samples. Now, the shape of a curve and the characteristics of the Gaussian distribution are what allowed statisticians to start thinking about significance. And this has to do, and perhaps is best related when we think about school grading or college grading or university grading. The assumption is that the performance in a test is almost always going to follow a normal distribution. The grade that you get will, and the frequency of certain grades, will typically have a characteristic shape with a small number of people getting very high grades and a small number getting very low grades, and the majority of students getting sort of middle of the road grades. Now, if we use that concept, then we can say that any grade that's within one standard deviation of the mean, let's say the mean on a test is 50%, and let's say the standard deviation is 15%. So that means the group as a whole will have a 75 or 50 to 65 as the upper one standard deviation, 35 lower half of the standard deviation. So those measuring within one standard deviation of the mean, between 50 and 65, would get an average score. Those getting higher than 2 standard deviations would get a very high score, and those having 3 standard deviations above the mean would get an extremely high score, and in fact would be very, very unusual or very rare. So if we were to apply this to a class of 400 students where they were graded, and if you were typically within this one standard deviation of the mean, say between 50 and 65% in the test, you would get a C. If you get between 65 and 80%, which is in the 2 standard deviation range, you might get a B. And if you get above 80%, which is now above 2 standard deviations, you would get an A. Similarly, if you were 1 standard deviation below the mean, you would get a D, and then any further, it's probably an F. So this is called grading to the curve, and of course the standard deviation can vary with a different test, and the upper limits and lower limits also varies. But the shape of the curve is almost always a Gaussian curve. Now, we use standard deviations and the number of standard deviations something or someone is above or below an expected distribution to assess the significance of that. Clearly, if someone gets an extremely high score, that's very significant. Similarly, if they get a very low score, that's also very significant. It's rare, it's unusual. So the point of the p-value is to determine the probability of obtaining a test, a score, a set of events, a measured weight or height or length that is at least as extreme as the one that was actually observed. So this allows us to assess whether a test score of 99% is really exceptional or whether everyone else got 99% and so it's not exceptional. In statistics, we talk about a null hypothesis and whether we accept or reject the null hypothesis. So with the p-value, we reject the null hypothesis when the p-value is less than the significance threshold. The threshold that's universally used, called alpha, is 0.05. This is at 2 standard deviations, above or away from the mean. In some cases, people use very extreme alphas, where they set the value at 0.01. That would be essentially 3 or 4 standard deviations away. If the null hypothesis is rejected, then it means that the result, the score, the height, the measurement, is statistically significant. So if the p-value is less than 0.05, the hypothesis is rejected and the result is significant. So what does that mean for more practical cases? Well, we can think of height again, where we take our sample of 250 people, and when you measure the average height of both men and women, it comes out to around 5'6" or 5'7", and that the standard deviation for human height is about 5 inches. So you can ask, what's the probability of finding someone who is more than 6 feet 10 inches? So remember, 5'7", one standard deviation takes you up to 6 feet. 2 standard deviations takes you up to 6'5". 3 standard deviations takes you up to 6'10". So if our alpha of 0.05 is being used, finding someone who is 6'11", that has a probability of less than 0.003%. And so that's extremely rare. And so you could use or structure your null hypothesis is if someone is more than 6'10", are they a member of the human species or not? Depending on what threshold, whether it's 0.05, 0.01, 0.003, you can reject or accept the null hypothesis. The choice of the alpha is often critical. By convention, it's 0.05, but it doesn't have to be. And to some extent, if someone justifies it in a reasonable way, they can choose any alpha they want. Now, in the case of human height, human weight, the distribution follows a characteristic normal or Gaussian distribution, and so we can interpret the alpha and the significance in terms of standard deviations. For other types of distributions, like coin flipping, it doesn't follow a Gaussian distribution, it follows a binomial distribution. We can use the binomial distribution to determine whether, say, a coin is fair or not. Fair being, if you flip the coin, will it have an equal probability of turning up heads or tails? Now, in this case, if we flipped a coin 20 times and found that it turned up heads 14 of 20 times, we can calculate the actual probability that it would occur using the binomial distribution, and we can come up with a value of 0.058. So based on that binomial distribution, can we determine if the coin is fair or not? If our alpha is 0.05, we would determine that this is a fair coin because it is above 0.05 in terms of the probability. If we chose an alpha of 0.1, we would determine it is an unfair or biased coin. The correct answer is hard to know, and to some extent it's a function of which threshold you've chosen. In that regard, it's important to be able to justify your choice of alpha and why it's used. Now, in the case of distributions, it's important to realize that not all distributions are the same and not are all equal. Most distributions are symmetric or Gaussian, but some data distributions are asymmetric or skewed. This can be seen, for instance, in the energy levels of alpha particles coming from radioactive materials. Anything with radionuclide decay follows what's called a Poisson distribution. Some data doesn't have a nice bell shape or a Poisson shape. Some of it's essentially rectangular in shape, and this is typical of purely random data. The types of distributions that are seen will affect what type of standard or average measurements you can obtain from them. This is showing a skewed distribution where you can see a peak somewhere on the left side and a long tail that extends far out to the right. In this case, I've marked 3 different lines. I've marked the mode, the median, and the mean. These are essential tendency measures, and they can vary depending on whether the distribution is symmetric or asymmetric. In a symmetric Gaussian distribution, the mean, the mode, and the median are all the same. But in a skewed distribution, they're different. The mean, which is the average value, can be significantly affected by certain small numbers of extreme values in the distribution. The median is the middlemost value, and it's determined by calculating both the mean and the mode. The mode is the most common value, and to some extent that's intuitive what we look at when we see either a symmetric or asymmetric distribution. We'll often identify the mode as the, quote, apparent mean. But remember, it's different, and there's a mathematical construct that you have to remember for mean, median, and mode.